In this lecture, we will look at the major process equivalences and look at when we have to use which equivalence. So we have seen quite a number of different behavioral equivalences, and the question that we could ask ourselves is when should we apply which equivalence and when should we apply which behavioral reduction? And there's a simple rule, namely strong bisimulation is always safe. So if you do not know what to use, restrict to strong bisimulation. Trace equivalence, on the other hand, is attractive because it can reduce the behavior much more, but it will not preserve the branching behavior. So as we've seen, it will not preserve, for instance, deadlocks. And with the branching behavior, we probably still recall these two transition systems where the moment of choice is different. With the example of the princess and the dragon, we have seen that we would not like to see these as equivalent, but from the perspective of trace equivalence, they are equal. Sometimes it happens that systems are not strongly bisimilar, and we would not like to use trace equivalence. And then a next best choice is failures equivalence. Failures equivalence preserves the deadlocks. It preserves some of the branching structure of processes, and in particular, it preserves equality under the application of ordinary process operators. If we now use internal steps, then the situation is slightly more complex. In general, the rule is that divergence preserving branching bisimulation is always safe to use. It removes all internal steps, but it preserves all the other structure of the behavior. If you're not interested in divergences, so we find it allowed to remove tau loops, then we can actually also apply branching bisimulation. And tau loops typically can mean that there is some internal activity going on that takes a lot of time, such that other actions will not happen very quickly. Weak bisimulation is for all practical purposes equal to branching bisimulation. So whether you use branching bisimulation or weak bisimulation in the settings up till now, it really doesn't matter. Weak trace equivalence, on the other hand, can be very attractive because it removes all the taus from the behavior. So if you have many taus but you would like to get rid of them, this is the equivalence to use. But it does not preserve the branching structure of the behavior, and that means that the behavior can really look different after applying this. So I use weak trace equivalence when the behavior is too complex and I still want to get a little bit of insight in it, but I always interpret the results very carefully. Okay, so what we should do is look at a few examples and ask ourselves, what is the naturally associated behavioral equivalence with these examples? Suppose that we have a complex system with lots of hidden actions that we want to get rid of, and we want to have behavior that is free from deadlocks. So the behavioral reduction should preserve deadlocks. What is the equivalence that we should use? Suppose we make software for a medical company and we build an X-ray detector. Then the X-ray can only be on when the situation is safe. So concretely, the activate beam, the X-ray beam, action can only happen between a shields on and a shields off action. And that's the important property that we want to preserve. What is then the natural behavioral equivalence that we would like to apply? Third exercise, if we want to reduce the behavior of transition systems as much as possible, but we do not want to remove internal behavior, and we also do not want to remove structural behavioral moments of choice, what is the natural equivalence to use? And the fourth exercise, if we have a system and that has a button with a sound alarm, and that causes an alarm to be sounded, and we want the alarm to be sound only within a finite number of actions after the sound alarm action takes place, what is then the appropriate behavioral reduction to apply that preserves this property? So we saw a few guidelines on when we have to use which behavioral equivalence. Thank you for watching. In the next lecture we will look at extensions of labeled transition systems with data, time and probabilities.